Glad you're still listening. Now we're going to talk about tangential and normal components of acceleration. So let's start with what we know in order to define acceleration rules. So oftentimes we're going to be starting with an r of t vector. And of course we know v of t, the derivative of my position vector, gives me velocity, which could be written this way as well. Now, if we take that and kind of unmultiply it using the chain rule, dr ds times ds dt, this is an equivalent statement. And of course, we know the derivative of r with respect to distance s, that is going to give us our tangent unit vector. And then we'll leave the ds dt. So right here, this is equal to my tangent unit vector. So what we want to keep in mind, and what we know from Calc 1 and Calc 2, is that acceleration is the derivative of velocity. So if I start thinking about acceleration, we'll call that a of t. We know that's the derivative of velocity with respect to t. Or we could say, since velocity is equal to t ds dt, we could say, well, this is the derivative with respect to t of velocity, or the derivative with respect to t of my tangent unit vector ds dt. So this is an equivalent statement. So acceleration's the derivative of velocity, right? Or the derivative with respect to time of velocity. And since we define velocity to equal the tangent unit vector times the derivative of distance with respect to time, we can redefine it this way. So we're going to take this and, kind of develop a way to restate, I should say, acceleration. So acceleration, a of t, I'm just going to rewrite this here and we're going to start working downwards. So if I wanted to find the derivative of this is a product. We would need to use the product rule. So we could say that a of t equals first times the derivative of the second plus second times the derivative of the first. So first we'll have t, the derivative of a derivative gives us the second derivative, so d2s dt squared plus the second ds dt times the derivative of the first, which is the derivative of t with respect to t. We can expand this piece right here a little further using the chain rule for differentiation. So I'm going to rewrite all my other pieces. T, d2s, dt2 plus ds dt times. And so I can rewrite this, and that by a previous definition or by breaking it down using the chain rule. That looks a little messy. We got dt ds times ds dt. So we want to recall something that we know, and we know that principal unit normal vector is equal to 1 over kappa dt ds. Or rather, we rearrange that, kappa times my principal unit normal vector is equal to dt ds. So I can sub that in for this one term right here. So rewriting, I've got t, second derivative of distance with respect to time. derivative of distance with respect to time. So dt ds is now equal to kappa times my normal vector, and then we have times ds dt. So ds dt times ds dt, that is ds dt squared. So we can further say that a of t, and I'm going to rearrange these components here. I'm going to put my t at the end. So I've got the second derivative of distance with respect to time times my tangent unit vector, plus, I'm going to pull these two together, and so I'm going to have kappa times ds dt squared. So I'll say kappa ds dt squared, and then I have my normal vector still multiplied through here on the end. So this is what we're going to use as our acceleration vector format, okay? So again, what is acceleration? When we have an object accelerated by gravity, brakes, rocket motors, we need to know how much of the acceleration acts in the direction of the motion. We have a direction of motion accompanying the tangent vector and a direction of motion accompanying that normal vector. One other piece that we want to consider is that no matter how the path of the moving object we're watching, no matter how much it appears to twist and turn in space, that the acceleration A is always flat in the same plane with t and n, our tangent vector and our normal unit vector. And all three, A, T, and N, all three of those vectors are in the same plane, and they're all orthogonal to B, our binormal unit vector. So let me restate the definition the way it's presented in your text. So pulling this in and considering this, acceleration, the acceleration vector, is written with this tangential component times the tangential unit vector plus a normal scalar component times the normal unit vector. So you see that a sub t is equal to the second derivative of distance with respect to time. So there's my a sub t is equal to this value, which we see right there in front of our t. And then a sub n is equal to kappa times the second derivative of, or I'm sorry, the derivative of position with respect to time squared, which we see that right up in there. So there's just different ways to write it, but you are going to want to remember this is my acceleration vector, and then we have these two components. And we can also think about writing those two components in this other method. So this definition above, we could remember it this way. A of t equals the derivative with respect to t of the magnitude of my velocity times my tangent unit normal vector plus kappa times the magnitude of my velocity vector squared times my normal vector. Either definition works, and it's always going to be set up this way. So just a little bit more to consider here. This a sub t measures the rate of change of v. Or rather, the change in speed. And a sub n, that normal component, that measures the rate of change for direction of v. Measures the rate of change for the direction of v. All right, so I've brought a picture in to just kind of help us visualize what's going on here. So we have our curve C. At some point, we have the tangent vector, the normal unit vector, and then this acceleration vector. And we see that tangential component and the normal component are being calculated as we defined above. Now, finding kappa is kind of labor intensive because we need to know V, the magnitude of V, T, the derivative of T, and then also the magnitude of that derivative. So we've got to calculate 5 things in order to find kappa. And since finding kappa can be so labor intensive, we have another formula here that helps us find that normal component of the acceleration vector. And so that is the square root of the acceleration vector's magnitude squared minus the tangential component of the acceleration vector squared. So make sure you understand these formulas and you have them written down. We're going to be using them and previous stuff in the following videos where we do some examples.